Welcome to this presentation on distributed concurrency control. We will explore how to manage concurrent access in distributed database systems. Managing data across multiple locations while ensuring smooth operations is a complex task, and this presentation will help you understand the key concepts. Let's explore the challenges in distributed concurrency. Data is partitioned across multiple nodes. This means that information is spread out, rather than being in one central location. There is network latency between distributed components. This refers to the delays in communication across the network. There is potential for partial failures in the system. Not every part of the system will fail at the same time. Some parts will fail while others continue to function. We need to maintain global consistency across all nodes, ensuring the data is the same, no matter where you access it from. We also have to handle clock synchronization issues. Since systems are in different geographical locations, keeping time synchronized is crucial. Now let's delve into distributed locking mechanisms. First, we have centralized locking. A single lock manager coordinates all lock requests across distributed nodes. This is a simple implementation, but it creates a single point of failure and potential performance bottleneck. Next is primary copy locking. Each data item has a primary copy at one site. Lock requests for a data item are directed to the site holding its primary copy, distributing lock management. Then there's majority locking. A transaction must acquire locks from a majority of sites to access a data item. This provides fault tolerance but increases message overhead and transaction latency. After that is distributed lock manager. Each site has its own lock manager that coordinates with other sites. This provides better scalability, but requires complex coordination protocols. We have timestamp-based locking. It uses global timestamps to order transactions. This avoids deadlocks, but may cause unnecessary transaction aborts due to timestamp conflicts. Lastly, we see quorum-based locking. It requires locks from a quorum of sites for read or write operations. Different read and write quorums can be defined to optimize for specific workloads. Now we will explore the two-phase commit protocol, often called 2PC. This protocol has two phases. In phase 1, the prepare phase, the coordinator sends a prepare message to all participating sites. Each site executes the transaction up to the commit point. The sites write recovery information to their logs. Each site responds with either ready, if prepared to commit, or abort, if unable to prepare. The coordinator collects all responses from participating sites, ensuring all sites are ready before proceeding to commit. In phase 2, the commit phase, the coordinator makes the global decision of commit, if all sites voted ready, or abort if any site voted abort. The coordinator writes the decision to its log. The coordinator sends the decision to all participating sites. Each site implements the decision and releases all locks. Finally, the sites acknowledge the completion to the coordinator, which ensures atomic commitment across all distributed sites. Now let's explore the limitations of two-phase commit. There is the blocking problem, where if the coordinator fails after the prepare phase, participants remain blocked until recovery. There's also a performance overhead, because it requires at least 2 round trips of communication. Resources remain locked during entire protocol execution, leading to extended locking. Finally, there are timeout issues. It is difficult to distinguish between slow sites and failed sites, which can cause confusion and delays. Now let's examine the three-phase commit protocol, known as 3PC. In phase 1, the prepare phase, the coordinator sends a prepare message to all participants. In phase 2, the pre-commit phase, if all vote ready, coordinator sends a pre-commit message. In phase 3, the commit phase, after all acknowledge pre-commit, the coordinator sends a final commit. Regarding timeout behavior, participants can make progress even if the coordinator fails. This protocol is designed to overcome the blocking problem of 2PC. Advantages include being non-blocking, so participants can reach consensus even if the coordinator fails. It also has improved availability through the pre-commit phase and better failure handling with timeout-based state transitions. Disadvantages include higher message overhead with 3 phases instead of 2, increased latency for transaction completion, and it is still vulnerable to network partitioning problems. Overall, there is a trade-off as it increases availability at the cost of performance. Let's discuss timestamp-based concurrency control. Each transaction labeled T sub I is assigned a unique global timestamp, labeled TS, then T sub I when it begins. For each data item X, the system maintains a read timestamp of X, which is the timestamp of the youngest transaction that read X. Also, a write timestamp of X, which is the timestamp of the youngest transaction that wrote X. A basic timestamp ordering rule follows that if reading T sub I in X, if the timestamp of T sub I is less than the write timestamp of X, abort T sub I because it is too late to read. Else, perform the read of T sub I in X, and set the read timestamp of X to the maximum of the read timestamp of X, and the timestamp of T sub I. This ensures serializability by ordering transactions based on their timestamps. The distributed implementation faces challenges in clock synchronization across multiple nodes, generating unique global timestamps, and handling network delays affecting timestamp order. Solutions include Lamport logical clocks for causal ordering, vector clocks for partial ordering, and hybrid approaches combining physical and logical timestamps. The Lamport timestamp generation includes a function. When sending a message to its destination, increase the local clock, set the message's timestamp to the local clock, and send the message to the destination. It avoids deadlocks but may cause unnecessary aborts. Now, let's compare the distributed concurrency control protocols. Two-phase commit, or 2PC, has the advantage of simple implementation, and it guarantees atomicity. Disadvantages include blocking on coordinator failure and extended locking periods. It is best used with reliable networks, in low-latency environments, and with short-lived transactions. Three-phase commit, or 3PC, has the advantage of being non-blocking, and it provides better failure handling. Disadvantages include higher message overhead and increased latency. It is best used in high-availability systems and in fault-tolerant applications. Timestamp ordering has the advantage of no deadlocks and reduced blocking. Disadvantages include clock synchronization issues and the potential for cascading aborts. It is best in read-heavy workloads and in systems with low contention. Distributed Multi-Version Concurrency Control, or MVCC, has the advantage of high concurrency for reads, and no read locks are needed. Disadvantages include storage overhead and complex version management. It is best used in online analytical processing, or OLAP systems, and in mixed read-write workloads. Finally, Paxos or Raft-based systems have the advantage of strong consistency and being fault-tolerant. Disadvantages include complex implementation and higher latency. It is best used in critical systems and consensus-critical applications. Let's explore real-world implementations. Google Spanner is a globally distributed database with strong consistency. It uses a true-time API for clock synchronization with bounded uncertainty. It implements two-phase locking for concurrency control. It also uses Paxos for distributed consensus. It provides external consistency, or linearizability, for transactions. Finally, it supports both read-write and read-only transactions, prioritizing consistency over availability. Amazon DynamoDB is a highly available, eventually consistent NoSQL database. It uses optimistic concurrency control with versioning. It implements conditional writes for atomic operations and provides tunable consistency levels, whether eventual or strong. It uses vector clocks for conflict resolution and supports transactions across multiple items and tables, prioritizing availability over consistency. To summarize, distributed concurrency control balances consistency, availability, and performance. Remember, no single protocol works best for all scenarios. The protocol choice depends on system requirements and workload characteristics. Future trends include hybrid protocols combining optimistic and pessimistic approaches, artificial intelligence-driven adaptive concurrency control mechanisms, and specialized protocols for edge computing environments. Recognize the trade-offs of strong consistency versus high availability, performance versus correctness guarantees, and implementation complexity versus system capabilities. For best practices, choose protocols based on data access patterns, consider network topology and latency in protocol selection, and implement proper monitoring and failure detection mechanisms. The challenge in distributed concurrency control is not just ensuring correctness, but doing so efficiently across unreliable networks with unpredictable latencies. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.